Important definition: code word. It is the block of bits at the output of the channel encoder. Code rate R equal to number of bits in message block by number of bits in encoded code word, that equal to K by N less than or equal to 1. RB equal to bit rate before channel encoding equal to 1 by TB. RB equal to bit rate or channel data rate after channel encoding equal to 1 by T naught. KTB equal to NT naught. R naught equal to N by K. RB that equal to RB by R. R naught greater than or equal to RB. Code efficiency. Code efficiency equal to K by N equal to code rate. Having weight of a code word W of X. Okay, now the W of X is equal to number of non-zero elements in the given code word. Example: having weight of a binary code word 1101 is 4. Having distance. The having distance between two code words is the number of locations in which their respective elements differ. Example: having distance between code words 10111010 and 011100 is 3. These three locations bits in two given code words are different. So the having distance between the two given code words is 3. Having distance between two given code words can also be defined as the having weight of the code word obtained by adding exclusive OR of the given two code words. Having distance between the code words 10111010 and 011100 is given by XOR operation that gives you 110010. Some properties of having distance between two code words. D of xy equal to having distance between the code words x and y. Then d of xy greater than or equal to 0 with equality if x equal to y. D of xy equal to dy comma x. Symmetry: d of xy less than or equal to dx comma z plus dz comma y. Triangle inequality. Minimum distance d minimum is the smallest value of the having distance between any pair of code words in the given coding system. It is also can be defined as the smallest having weight of non-zero code words in the coding system if all zeros is a code word in that coding system. Example: linear block codes. Relation between d minimum and detection and correction capabilities of the code. Capability: detect up to s errors per word. Condition: d minimum greater than or equal to s plus 1. Detect and correct up to t errors per word. Condition: d minimum greater than or equal to 2t plus 1. Correct up to t errors and detect s greater than or equal to t errors per code. Condition: d minimum greater than or equal to t plus s plus 1. Representation of codes for linear codes n comma k or n comma k comma d. Representation is used n equal to number of bits in the encoded word, k equal to number of message bits, d equal to minimum distance. For non-linear codes n comma m or n comma m comma d, representation is used n equal to number of bits in the encoded code word, n equal to 2 power k equal to total number of different code words in the code. Singleton bound for n comma k block code. D minimum is less than equal to n minus k plus 1, 2 less than equal to k less than equal to n minus 2. The block code in which d minimum equal to n minus k plus 1 is called maximum distance code, MDC, or maximum separable code. Example: repetition code n comma 1 comma 2, single package codes n comma n minus 1 comma 2, and some RS codes non-binary. Linear code: a code is said to be linear when the addition of two different code words produces another valid code word in the same coding system. Linear block codes. Okay. B0, B1, B2.
Linear block codes B0, B1, and so on Bn minus k minus 1 is called nk n hyphen k parity bits. M0, M1, and so on mk minus 1 k message bits. M0, M1, and so on mk minus 1 k message bits or B0, B1, B2, n k parity bits. Any model can be used. Structure of code word of a block codes: G bar equal to ik bar colon p bar k by n equal to generator matrix. G bar is not unique. That is, a code may have more than one generator. The generator matrix G bar is said to be systematic when it is in the form G bar equal to ik colon p bar. That is, G bar is said to be systematic when it has a rank equal to k. Every code need not to have systematic in G bar. There is another way of expressing the relationship between the message bits and the parasitic bits of a linear block code. H bar equal to P bar transpose colon in minus k. H bar G bar transpose equal to P bar transpose the colon in minus k. Ik and so on, P bar equal to P bar transpose plus P bar transpose, that is nothing but 0. That is nothing but 0. So P bar transpose plus P bar transpose is 0. H bar G bar transpose equals 0. H bar G bar transpose whole transpose equals 0. G bar H bar transpose equals 0. X bar equal to M bar G bar. X bar H bar T equal to M bar G bar H transpose. X bar H transpose equals 0. Parametric equation. The matrix H bar is called the parametric matrix of the code. H bar is said to be valid when the following two conditions are satisfied. H bar G bar transpose equals 0. Rank of H bar is n minus k. The generator matrix G bar used in the encoding operation in the transmitter. The parametric matrix H bar is used in the decoding operation in the receiver. Properties of linear block codes LBCs. An LBC remains unchanged if the generator matrix is subjected to elementary row operations. Suppose you can form a new code by choosing any two components and transposing the symbols in these two components. This gives a new code which will be also an LBC, or all two block codes are equivalent if they are same except for a permutation of the code word components with generator matrices G bar and G bar dash. G bar dash can be obtained from G bar, hence G bar and G bar dash are generator matrices of two LBCs. Every generator matrix G bar of an LBC can be reduced by elementary row operation and column operation to the following form: G bar equal to IK bar cross K by K colon Pn minus K by K bar equal to systematic form or row echelon form. So every LBC is a systematic code. Relation between D minimum and H bar of an LBC. D minimum equal to minimum number of columns of H bar or rows of H bar transpose that sums to 0. A linear block code that corrects all burst errors of length L or less must satisfy n minus k greater than or equal to 2L. Syndrome decoding. When the encoded word is transmitted through a noisy channel, some error will occur in the received code word. Let this error code word is denoted by Y bar. X bar used to noisy channel gives you Y bar. That means Y bar equal to X bar plus E bar. X bar equal to Y bar plus E bar plus indicates XOR or modulus to addition. The ith element of E bar is 0 if the corresponding element of Y bar is same as that of X bar. On the other hand, the ith element of E bar is 1 if the corresponding element of Y bar is different from that of X bar. The algorithm commonly used to perform this decoding operation starts with the computation of a vector called the error syndrome vector, or simply the syndrome S bar. S bar equal to Y bar H bar transpose. Based on the obtained syndrome, a particular error pattern will be selected by the channel decoder to correct the errors. Properties of syndrome. The syndrome depends only on the error pattern and not on the transmitted code word. S bar equal to Y bar H bar transpose. X bar plus E bar to H bar transpose equal to X bar H bar transpose plus E bar H bar transpose. E bar H bar transpose X bar H bar transpose equal to 0. Property 2. All error patterns that differ at most by a code word have the same syndrome. EI equal to E plus XI, where I equal to 0, 1 and so on 2 power k minus 1. For k message bits, there are 2 power k distinct code vectors denoted as xi bar, ei bar h bar transpose equal to e bar h bar transpose plus xi bar h bar transpose, that equal to e bar h bar transpose, which is independent of the index I. The set of vectors ei I equal to 0, 1 and so on 2 power k minus 1 is called a coset of the code. Each coset consists of 2 power k different error patterns and these all 2 power k error patterns of a particular coset produce same syndrome. Property 3. The syndrome S bar is the sum modulo to sum of those columns of a matrix H bar corresponding to the error locations. Property 4. With syndrome decoding, an n comma k linear block code can corrupt up to t errors per code word provided that n and k satisfy the Hamming bound. What is the Hamming bound? Means 2 power n minus k greater than or equal to sigma I equals 0 to 2 column matrix of ni. Column matrix of ni is a binomial coefficient that equal to n factorial by n minus I factorial into I factorial 2 power n minus k equal to total number of possible syndromes. The significance of the above bound is that an n comma k linear block code is able to correct up to t errors when the total number of syndromes must not be less than the total number of all possible error patterns with errors up to t locations including no error condition. The decoding algorithm may proceed as follows. For the received vector y bar, compute the syndrome S bar equal to y bar h bar transpose the coset characterized by the syndrome S bar. Choose the error pattern with the largest possibility. Call it E naught bar. For output, that is for corrected code word, compute the code vector x bar equal to y bar plus E naught bar. Hamming codes n comma k linear block codes that have the following parameters are called Hamming codes. Block length or code word length n equal to 2 power m minus 1. Number of message bits k equal to 2 power m minus m minus 1. 2 power m separate to then kendra minus m minus 1. Number of parity bits n minus number of parity bits n minus k equal to m, where m must be greater than or equal to 3. Okay, now Hamming code for 7 comma 4 Hamming code n equal to 7, k equal to 4, m equal to 3, m bar equal to m naught, m1, m2, m3. There is nothing but message bits. B bar equal to b naught, b1, b2 is called parity bits. Then x bar encoded code word equal to m naught, m1, m2, m3, b naught, b1, b2. This is the one way of showing the relation between b naught, b1, b2 and m naught, m1, m2, m3. We can also form the Hamming code by changing the places of b naught, b1, b2 and m naught, m1, m2, m3. For example, b naught plus m naught plus m1 plus m2 equal to 0. b1 plus m naught plus m1 plus m3 equal to 0. b2 plus m naught plus m2 plus m3 equal to 0. b naught equal to m naught plus m1 plus m2 plus means XR. Okay, na b1 equal to m naught plus m1 plus m3, b2 equal to m naught plus m2 plus m3, b naught, b1, b2 equal to row matrix of m naught, m1, m2, m3, column matrix of, in that column, first column 1110, second column 1101, third column 1011. P bar equal to first column the 1110, 1101, 1011. G bar equal to 10001000010, 001 colon with 1110, 1101, 1011. H bar equal to 11101011011, 1 colon with 100010001. Message word, code word, weight of the code word. From the above table, you can say D minimum for the 7 comma 4 Hamming code is 3. Hamming codes have the property that D minimum equal to 3 irrespective of the value of the assigned to M. that is for any n comma k Hamming code d minimum equal to 3. So we can represent Hamming codes as n comma k comma d implies 2 power m minus 1, 2 power m minus m minus 1 comma 3, t less than or equal to d min minus 1 by 2, or t less than or equal to 3 minus 1 by 2, t less than or equal to 1. So Hamming codes can be used to correct all 1 bit errors. Hamming codes check for Hamming bound 2 power n minus k greater than or equal to sigma I equal to 0 to t ni, n equal to 7, k equal to 4, 2 power n minus k equal to 2 cube equal to 8 for t equal to 1, sigma I equal to 0 to t ni equal to sigma I equal to 0 to 1 ni equal to n factorial by n factorial 0 factorial plus n factorial by n minus 1 factorial into 1 factorial, that equal to 7 factorial by 7 factorial plus 7 factorial by 6 factorial equal to 8. So for t equal to 1, 2 power n minus k equal to sigma I equal 0 to t ni. For t greater than 1, 2 power n minus k less than sigma I equal to 0 to t ni. This means that Hamming codes are single error correction binary perfect codes. Syndrome and error patterns. H bar equal to 311 110 101 011 100 011 010 001. Syndrome. When syndrome S bar equal to 311, then most probable error pattern is 1 0 0 0 0 0. When syndrome S bar equal to 110, then most probable error pattern is 0150. Miscellaneous. Frequency range of voice signal is 300 Hz to 3.4 kHz. Frequency range of audio signal is 20 Hz to 20 kHz. Frequency range of TV signal is 0 to 4.5 MHz. Copper cable kHz, coaxial cable MHz, waveguide GHz, optical fiber THz. Coaxial cable is also used for connection making as connector BNC, Bayonet Navi connector, and TNC, terminated Navi connectors. Amplitude distortion. This type of distortion results from production of new frequency in output which are not there in the input signal. These new frequencies are caused due to non-linearity of active devices. Frequency distortion. This type of distortion exists when signal component of different frequencies are amplified differently. It is caused by stray capacitances and stray circuit capacitances. Phase distortion. It results from unequal delays of the signal of different frequencies. Note: capacitors and inductors cause frequency and phase distortion, but not the amplitude distortion, as they are linear elements. Super heterodyne receiver. Super heterodyne receiver is used in AM receiver circuit. AM radio broadcasting utilizes the frequency band 535 kHz to 1605 kHz for transmission of voice and music. Carrier frequency allocations range 542 kHz to 1600 kHz with 10 kHz spacing. The baseband message signal is band limited to 5 kHz. Intermediate frequency used for AM is 455 kHz. Frequency of local oscillator is given by, for down conversion, FLO equal to Fs minus Fif. For up conversion, FLO equal to Fs plus Fif, where Fs is the carrier frequency of the desired AM radio signal. Up conversion is preferred because of requirement of less tuning range. For capacitor, polarization is vertical and wave propagation is ground wave. The tuning range of local oscillator is 995 kHz to 2055 kHz. An AM signal is transmitted at a frequency FLO plus FIF is called image frequency. For an AM signal transmitted at frequency Fs equal to FLO minus FIF. So image frequency FSI equal to FLO plus FIF. Image signal rejection ratio alpha equal to root over 1 plus rho square q square, where q is the quality factor, rho equal to FSI by Fs minus Fs by Fsi. In order to reject image frequency, bandwidth of RF amplifier should be BC less than BRFS less than 2IF, where BC is bandwidth of AM radio signal, BRF means bandwidth of RF amplifier, FIF means intermediate frequency. FM radio broadcasting utilizes the frequency band 88 to 108 MHz. The carrier frequencies are separated by 200 kHz and peak frequency deviation is fixed at 75 kHz. Intermediate frequency FIF in case of FM is 10.7 MHz. Polarization is horizontal, wave propagation is space wave propagation. In case of TV, signal picture carrier is VSB-FC modulated, color subcarrier is UAM modulated, and sound is FM modulated.